We wanted to fix a curve, a smooth, complex, compact algebraic curve, and we fixed a finite collection of points, A, in there. So in this talk, I'll mainly look at the case where I just fix one point, and we wanted to fix an irregular class theta at that point. So this is the basic data that we want to fix, and we'll call that triple sigma tilde, and I'll often call that an irregular or a wild curve. So basically the moduli or the deformations of these control the base of these bundles of isomonogamy deformations. So it's possible to enrich the moduli of curve with marked points by adding on these irregular classes. So recall that so we had a point of a curve, and so we had this picture of the so the circle of the directions, this partial, so we did this real-oriented blow-up of the curve at the point A, and this gave this circle of directions, so a point of that corresponds to a real direction here, and an interval there will match up with a small germ of a sector at the pole. And then we had this cover I, the exponential local system, which is a cover, and then we wanted to pick an irregular class, and this corresponds to fixing a finite number of circles plus a multiplicity of each of these. So we're actually fixing a finite subcover, so a finite collection of circles, which I'll call a finite subcover. So this is something like the union from 1 to k of certain circles qi. And then we wanted to fix a multiplicity for each of those. So theta is the extra choice of an integer greater than or equal to 1 for each circle. So it's something like the sum ni qi, like this, from 1 to k still. So that's the basic data that we wanted to pick. And if you look in particular examples and choose a coordinate, often choosing theta is equivalent to fixing some diagonal matrix, sort of q1 up to qk, repeated with their multiplicities, where in the untwisted case you would have something like qi is an element of z inverse cz inverse, like this. And then we'd also have the twisted case also, which straightens out after choosing a root of z. Okay, so we fix this irregular curve, and then we're supposed to define a Poisson wild character variety. So we want to basically talk about how to define that today, and then move on to the quasi-Hamiltonian perspective afterwards. So we need to look more precisely. So these occur because if you look at solutions of equations, they'll have things like e to the q occurring in solutions. And so we want to look at the different growth and decay of these functions as you go towards the pole. So what do we want to do? So we've fixed this finite subcover. And we want to define the points of maximal decay. So the points of maximal decay. So like the POMs. So I'll sometimes call them apples, because POM is the French word for apple. People often ask this. So and the POMs is a subset of I. It's a finite subset of each circle, and it's just the points of maximal decay of the function e to the q. And so the apples of q in a circle q. So this is a particular the circle. So here's q, and this is a cover of our circle of directions. So I want to look at the function x of q here. So on a sector on an interval there, that corresponds to a sector at the pole, so I actually have a function there, and you walk around the circle and look at the points where this has maximal decay. So this is just the points of maximal decay of e to the q. So it's a finite set in each circle, so it's empty if and only if it's the tame circle. So if and only if you're in the tame circle 0. Otherwise, you define the irregularity of a circle to be the number of apples, the number of poms. So if you go back to Stokes's picture, so this is the picture for taking the irregular type Q to be x to the 3/2, where x is the pole is at the infinite point, and so x is 1/z. So the points of maximal decay are these things A, B, and C, and the points of maximal decay will be the big A, B, and C, and the points of minimal decay will be the small A, B, and C. So these are the points, the singular directions as well in this example, but we'll get to that in a moment. So the first thing we need to define is the poms, and then we need to define the Stokes arrows. So now we have a pair of circles, and these are arrows in the fibers of the map to the circle at the base. So suppose I have a circle like this and a circle like that, and these are both over the circle at the base. The basic example for panel of A2, you might have something like x cubed and minus x cubed like this. And so this is where x is 1/z, and you have the pole at the infinite point. So the Stokes arrows, so you define a partial order in the fibers. And so you'll say, so Qi is, so there's various different notations in the paper. There's this thing following the paper of Michel Daudet-Pichot, which is this sort of curly less than, which is hard to draw. So instead I'll use the notation from the Martinet and Remis paper that I can't find the latex of, but it's this bold double arrow like this. So if I have a direction D, so the direction at the base, define a Stokes arrow, or there exists a Stokes arrow between the points of the fibers. So let's write this differently. Let's say I and J. So I and J are points of the fiber, ID. So this is I, the union of these two circles. And I have corresponding functions Qi and Qj nearby on the sector around D. So I have this point D here. And you'll say that I is less than D like this if the difference is a point of maximal decay. If I minus j is a pom. So this relates to the fact that x of qi minus qj has maximal decay. Okay, so there's a finite collection of arrows. So we're looking at the relation between x of x cubed and x of x minus. So x of x cubed divided by x of minus x cubed. So you get things like x of 2x cubed and x of minus 2x cubed. So you basically get 6 arrows, and they alternate between going up and down. So there's 6 points. If I'm going to get this right. Okay, so there's arrows that go down and then up, and then down, and then up, and then down, and then up, like this. These are the, so each of these corresponds to an arrow from J to I, going from the one which is the biggest to the one which is the smallest. So this is J here, I guess. Okay, so there's a finite number of arrows between any pair of distinct circles. Okay, so we'll use these to define the Stokes groups. So our aim is basically to write down the axioms that we get. We have this graded local system, and we want to glue it onto the local system of solutions on the interior of the curve. And our aim is to write down what the axioms are. And the key point is that the monodromy, when you glue on two different directions, has to be in these Stokes groups. So that's the reason we want to define these. Yeah, so if I have a vector space which is graded by ID, so I have this finite subcover, and I look at the fiber of that, and suppose I have a vector space which is graded by this the fiber of this cover here. So for instance, if I have a fiber of a graded local system like I had before, then we can have a look to see the Stokes arrows between the points of here, and that determines a subgroup of GL V0 of D. So we define, so e.g., suppose this is graded V0 of D is the sum of V0 D I for I in ID, then we'll define the Stokes group. So we look at the representations of the quiver given by the arrows in the fiber. So this is just exp of the sum of the homomorphisms from V0 DI to V0 DJ. So I look at the graded pieces and I sum over all of the Stokes arrows which occur in that fiber. So it's as if I've got I is connected by a Stokes arrow from J. So I've got this around the wrong way, so I want to go from J to I. The arrow here is the direction in which the map goes. And so because this is a partial order on the fibers, this direct sum is a nilpotent Lie subalgebra of the endomorphisms of this graded vector space. And we're just taking the exponential of that into the group. And so we get a unipotent subgroup of GL, or all automorphisms of V0D. Okay, so we have a group for each such graded vector space. And generically, this group will be trivial. We have special directions where we get a Stokes arrow. These are the singular directions. So I'll call these A. It's like it's where the apples fall or something, but they're often called anti-Stokes directions, but there's this, half the people call them anti-Stokes and half the people call them Stokes, and there are people who call them anti-Stokes directions in their papers, and then in their talks they call them Stokes directions. And so I'll call these the singular directions, which is what Stokes called them. The problem is that people try to understand Stokes' work afterwards, and the people who first use the word Stokes direction use it in perhaps a different sense than you might have had directly from what Stokes did. So Stokes called them singular directions, and so we'll stick to that. It's the clear geometric thing that happens. So it's A is a finite subset of the directions. So I fix this finite subcover I, and you look at the Stokes arrows, and you just look at the subset of the base below the non-trivial Stokes arrows. And so here you would get 6 points like this. So these are the points below the Stokes arrows. So in Stokes' picture, for the Airy equation, these are the 3 directions marked with these points A, B, C, D here. So if we call those the anti-Stokes directions, then the Stokes directions are where you have this change of dominance, and we'll get to that when we talk about Stokes filtrations in a moment. But first of all, I want to get to the Stokes local systems. Okay. So we come back to this picture that we have a connection on a curve. We define this graded local system in a small punctured disk around the pole. And we also have the local system of solutions. So we get this, connection, so an algebraic connection on our curve gives us, so here it's just sigma minus a. We're looking at the case with 1 point. So we get v over sigma o. This is the solutions that we looked at right at the start. And we also get the graded local system over this circle. And this is homotopy equivalent to this halo. So we have this direction here. We have some curve like this, and we did this real oriented blow up. And so this is sigma hat, which is the real blow up of sigma at the point A. And so I've replaced the point A there by this circle of direction. So I get a surface with boundary. And so there's this neighborhood here, the halo. I'll call this H. So H contracts onto this circle. It's an annulus, and we'll call this the halo. So on this halo, we have V, and we also have V restricted to H. So you have these two local systems there, or we could restrict V all of the way to this circle. So we have two local systems on the circle, and the basic point is that the connection gives us a canonical way to glue these local systems together, an isomorphism of local systems away from the singular directions. And that's the basic fact about sort of the topological fact that all of these analytic procedures of multi-summation gives you. So the basic fact, the connection, the nabla, gives you a way to glue V to V0 over, let's just say, D minus A. So this has an irregular class, and I'm taking I here to be the finite subcover determined by the irregular class. So I'm taking the singular directions determined by that class. So we have a finite collection of singular directions like this. We have a way to glue these two local systems together. It could well be that the local systems globally aren't isomorphic. So if we go back to this airy picture, this is a differential equation on the complex plane. There's no monodromy, and so the local system of solutions is completely trivial, but the graded local system has this business of switching over, so it's definitely not trivial. So in particular, V and V0 are not isomorphic as local systems on the circle, but they have these preferred isomorphisms away from the singular directions. So to express the object that we get, we could take a second copy of the halo and glue it down here away from a tunnel which occurs, or I could take a copy of the circle and glue away from the points, and then it's possible to look at the fundamental group of that space and define local systems there. But it's easier just to do a tangential puncture in the interior of the curve, slightly like this. And so I'll have V in the interior of the curve, and I'll just take V0 in the halo, and then the effect to glue these together says that on each interval here, between the consecutive tangential punches, there's a canonical way to glue V to V0. So this gives us a local system, a bundle with flat connection, V on this curve sigma tilde, which is got by taking these tangential punches. And so this curve is now sigma tilde, which is sigma hat minus the tangential punches. And there's one of those for each singular direction. So these could be described as E of D for each D in A, where E of D means to take a point D and go slightly in, and so this will be E of D like this. Okay, so we get this auxiliary curve with these tangential punches, and the basic object that we get is a local system there, and it has the property that if I restrict it to this halo, it has to be graded. So it has these axioms. One is that V restricted to the halo, or the boundary if you prefer, is graded. So it's I graded, so of class theta. So the multiplicities of the pieces is given by the multiplicities that we picked at the start. So in particular, it's graded by our finite subcover I, and each piece has dimension equal to the corresponding integer n of I. And the second axiom, which is trickier, is about the monodromy of the local system around the punches. So if I choose a base point, say here, and have a small loop that goes out and around a tangential puncher and back, well, this monodromy gives me an automorphism of the fiber of V0 here. So that's a graded vector space. So I have a Stokes group in the fiber. So we can just put that the monodromy around here has to be in the corresponding Stokes group. So let me call this loop. So let me change D to be over here. Let me call this loop gamma of D. So the monodromy of V around gamma of D is in corresponding Stokes group Sto D. And this is well defined because at the base point we do indeed have a graded vector space. And that's it. That's all the axioms we need to have. That this is for all D in A, for all singular directions. So this defines a groupoid, the Stokes local systems with class theta on our curve. And it has this nice property that they are local systems. And so we can just take the monodromy of these, and then we get to the presentations that we wanted to get to. And it gives an intrinsic way to understand what Birkhoff did and all of the extensions by Yerkatz and Martinet and Remis and Lode, Richaud and others. Okay, so now I want to draw an example and get to the Stokes representations, which are the monodromy of the Stokes local systems. Are there any questions about this? Is it roughly clear? Is there?
I don't know. So this is a way to attach to an asymptotic an actual solution.
Now I'm trying to write down the axioms of the category or the subgroup or the category of local systems with a fixed irregular class. So it will become more concrete in a moment. We had that picture at the start, and we had tame connections, and this became local systems, and we then chose a base point, and that became the representations of the fundamental group, and then we chose generators of the fundamental group, and that became sort of matrices whose product is equal to 1. Okay, so I've just defined the wild version of the local systems, the completely intrinsic perspective there, and now I'm going to take the monodromy of those to get the analog of like the representations of the fundamental group, these Stokes representations, and then we'll choose generators of the groupoid which occurs there to get to these explicit relations, explicit presentations of the wild character varieties, examples of which go back to Birkhoff in 1913 or so. So this looks slightly abstract, and it is abstract, but it's supposed to be because it's the wild analog of the abstract approach to the intrinsic approach to the topological data of connections through local systems. It will It will become more concrete now, and we'll write down some products of matrices as equal to 1. And you'll see that it's the same thing that you know, but now we have an intrinsic perspective, and we can see what the choices are when we vary all of the structure of the irregular curve, how to define isomonodromy properly. You need to have a coordinate-independent perspective, or at least prove that it's independent of coordinates, and this will do that. Or, yeah.
So there is no way to extend this local system over these new points that you added in?
It could be that the Stokes data is trivial, but in general there will be monodromy. If I look at this in the tame case, then there's no tangential punctures at all, and it's exactly the usual picture that everybody knows. So this is one way to describe the extra data that you need to have. It's this way to glue the graded local system to the solutions in the middle V, and this is a topological description of what analytically people do. In Stokes's paper, he does start off with a formal solution at infinity and explains preferred actual solutions which are determined by those formal solutions, and that became the Borel summation and the multi-summation perspective, and that is a way to pass from a formal solution to an actual analytic solution. And what that says topologically is that there's a way to glue the graded local system to the local system of solutions V in the interior of the curve.
And another thing that I didn't understand is where did the ramification come in, or this was the case without ramification?
So the ramification comes in. I'd have this circle here, I'd have this cover I. So if that cover is trivial, if it's just circles that map isomorphically down, then it's untwisted or unramified. But if it's like in Stokes's picture, if there's a circle which is like a degree 2 cover, that's expressed in the fact that the local system here, which is still a genuine local system, but the grading of it is twisted. So it's a well-defined local system, but it's divided into these two pieces, and as I analytically continue those around, they'll get swapped over if I have a cover which is twisted. And this will add to complications in the quasi-Hamiltonian picture when we get to that. It's a twisted quasi-Hamiltonian space and not a direct quasi-Hamiltonian space. Okay, so there's two things I want to do. I want to give an example, and I want to get to Stokes representations. So this is just the monodromy of the Stokes local system. So just like a monodromy representation is the monodromy of a local system, or the monodromy of the original connection. So we want to describe the space where these live. So basically, you'll get a representation which is in Hom S pi G. And this is a subspace of Hom pi G. So I can tell you straight away that pi is just the fundamental. So here I'm looking at the case with one marked point. But in general, I'll have a. Yeah, so we'll choose a base point on the boundary in the halo. So I have some points here, B. So in the case with just one of these, so I'm looking at the fundamental groupoid of this auxiliary curve sigma tilde, so with the extra punctures, with this base point B. In general, I'll pick one base point on each such boundary circle. So it'll be a groupoid and not a group. So here I can talk about like the wild surface group, which is this finitely generated group which sort of generalizes the fundamental group, which should not be confused with the Martinet-Ramis wild fundamental group that sort of puts everything together. This is a discrete group. It's just the fundamental group of this surface with extra punctures. So if I just take the monodromy of a Stokes representation, it is a local system on sigma tilde. So its monodromy gives me a point here. So then we just need to look at the subspace of this, of the representations which obey the axioms that we had. So to define, so then we look at the subspace, the sub-variety of all. Right, so we've got sort of all of the representations. We want to define what this S is. What are the Stokes representations amongst all of the representations of this curve having extra punctures? And you just need to translate over the axioms that we had before. Yeah, so we get, there's a grading condition. And there's the Stokes condition. So I'll spell out the grading condition in a moment. The Stokes condition is the obvious thing that if I have a path that goes from the base point around an extra puncture, it has to be in the corresponding Stokes group translated back to the base point. Okay. So let me do an example. So this is sort of pan of A2. The standard lax pair, which I guess is due to Garnier and Jimbo Miwa. So this is where you have this I is x cubed union minus x cubed, both circles with multiplicity 1. So the pole is at the infinite point, so you get this circle there, so this is partial. And then you have to compute what the singular directions are. So basically, I think that there are 6, as we looked at before. So you get some picture like this. So the halo is at the outside now, and so we'll have, like, you know, V in the interior here. The local system is trivial because there's no other poles at all, and so this is like, you know, sort of the constant copy of C2. So this will end up being a space I want to call B. So this will be the Stokes representations in this case, Hom S pi G. So here G is just GL2. So yeah, we basically have a base point, and you look at the monogeries, and so we end up with something like H, S6, S5, S4, S3, S2, S1 equals 1, where these alternate by between being in the upper and lower triangular unipotent group, and so something like S odd. S odd is in 1 star 0, 1, and S even is in 1 star 1, 0, like this. Right, so I think the space is just that you get. Okay, so this part is basically in the big cell of GL2, and so this part is determined by the matrix entries of these, and so you see it's of dimension 4. This is dimension C4, and it has what will turn out to be a quasi-Hamiltonian action of the torus. So then we'll get the space you're actually interested in is the reduction of this, so M, yeah.
Where is H?
Sorry, yes, H is in a torus, and so H is in the group which I'll generally call H, which here is isomorphic to T. So T is the graded automorphisms of the fiber, so this is like V0B, and so this is isomorphic to C star squared. That's the formal monodromy. So I have a loop that goes something like around here. This is the H is the monodromy around there, and then there's loops like this, which give you the Stokes data somehow or other. There's a certain presentation that you can pick that will give you this monodromy relation here. The fact that this is a six-punctured disk. Okay, so MB, so if you want to do this properly, this is a moduli space of framed Stokes representations where we look at the moduli of Stokes-Dokel systems plus an isomorphism between the fiber here and a standard framed space. So we have a standard fiber. So F is just the direct sum of like C to the theta of D. So where D is in the fiber of I at the base point B. So I have the base point B, I have this cover, and I look at the fiber of that, and I have a number here, which is the corresponding multiplicity upstairs, and I just take the direct sums. So that's isomorphic to C to the n, but it's graded in that it's broken up into these pieces. So we want to look at the set of isomorphism classes of pairs of a Stokes-Dokel system plus a isomorphism with the fiber of the local system and the standard fiber here. And then you see that there's a natural action on here of the group of graded automorphisms of the standard. So H is just gr-ort of this. So as a group, it's isomorphic to the product of GLNI of C repleted with the ramification of QI. So it's some block diagonal subgroup, and it embeds as a block diagonal group of GLNC. So this group naturally acts on here because this is the moduli space of framed Stokes-Dokel systems. And in this particular case, it becomes the action of the Maxwell torus T acting by diagonal conjugation on this space. So MB is just the quotient of this. This is B modulo T. And this one will turn out to be an algebraic Poisson space, and the symplexic leaves are these things MB of Q contained in MB. And this is just where you fix the value of here. So really you want to fix the conjugacy class of H, but H is in a torus, so it's just the same as fixing a point, and you'll fix it to be in something like H is equal to Q inverse. Okay, but in this example you can... So here it's possible to make it all explicit. Sorry.
H is QP for some other P because it's in C stars.
No, because this product has to be equal to 1 and the determinant of all of these is equal to 1, it fixes that. So here, MBQ, so basically you can compute all of this explicitly. And there's even a formula for what the product of these triangular matrices are, which goes back to Euler, the Euler continuum polynomials. And then you just need to compute this adjoint action of the torus. So it's an action of C star, which is easy to compute. And you get this thing that this is isomorphic to this cubic xyz plus x plus y plus z is equal to b minus b inverse. So b is a complex, an invertible complex number such that b squared is minus q. So this equation first occurs in a paper of Flashko-Newell using a different lax pair for panel of A2, but it's easy to prove that it's isomorphic, and so you get the same formula. But it's possible to do this for an arbitrary order of the pole, increasing any even number of Stokes data, and then you can look at lots of other examples, also having these products of triangular matrices.
Also, in the case when there is no boundary, the symplectic structure comes from dimensional reduction from this infinite dimensional picture, right? But in this case where does how does one describe the Poisson structure?
Right, so that's the kind of the aim of the rest of the talk. So in the case without poles, there's this T-bot picture, which you have this infinite dimensional symplectic equation, and you're basically looking at the space of flat connections, and there's this nice fact that the moment map, the curvature is a moment map for the gauge group. And so the flat connections is like mu inverse of 0 modulo the gauge group, and so it is a symplectic quotient, and so you see that the modulo space of flat connections will have a symplectic structure. So in my thesis, I extended that to the irregular case, and then there's a question of trying to understand it more algebraically. So in the original Atiyah-Bott picture, there are various different perspectives, one perspective of which is this quasi-Hamiltonian perspective of Alexeyev, Malkin, and Weinbrenken. So basically I went through all of the different perspectives and found the one which I understood the best, and then generalized that to this irregular case as well. So at the end of the day, we'll get these spaces as finite dimensional quasi-Hamiltonian quotients, which is a more algebraic approach than the infinite dimensional analytic approach that came before. So I'm skipping over this step of extend that, but it's in my thesis, and it's in a paper which is in Advances in Math in 2001, and I posted it on the archive yesterday or something. Well, I posted it on Friday. I was hoping, so the archive has numbers, so I messed up that it was published in 2001, so I was thinking if I posted it in January 2020, then the archive number would be 2001. So I did post it, but I posted it after the deadline, so it actually comes up as 2002, but it does say, Friday the 31st of January 2020, but it's got the 2002 number for some reason. But anyway, there is an analytic story, and the analytic story was upgraded in this paper with Bickard to not just be a complex symplectic quotient, but to give the full hyperkähler metrics and the actual precise analytic construction of the modulo spaces as hyperkähler spaces, which are often complete. But here I'm more looking at the more algebraic perspective, how to obtain these as finite dimensional symplectic quotients. So let me sort of state the result that we want to get to. So maybe I'll state it in the untwisted case first. Let's go back to the general picture. So let's define the wild representation variety to be this space Om S pi G. So this is the space of Stokes representations. If you like, the wild representation variety. I'm just trying to extend all of the terminology that people have in the usual tame picture. So it's a moduli space of framed Stokes, of framed Stokes local systems of irregular class theta. So in general, I may have M marked points, and I'll choose a base point at each of those. So we'll define this group H, which is sort of H1 cross HM. So HI is the ort at so the ith marked ith base point, which is at the ith boundary. So there's some block diagonal subgroup of GLNC at each of the points, and we just take the product of each of those, and so HI is acting on R. Okay, so we have a space having a group action. Now, we didn't write down what the Stokes the grading condition is. Maybe I should do that because it'll be easier whilst it's on the board. So the grading condition. So first of all, one, if it's not twisted, it just says that H, HI, which is like the representation around the ith boundary with respect to the base point BI. So I just have this circle. I have some halo, and I may have some tangential punctures. I have this circle D at a base point B. I just look at the monodromy around there, and I call that HI. That has to be in this group H. So it has to be a graded automorphism in the untwisted case if the cover is not twisted. And then you need to work out how to extend that. Where does the monodromy of a graded local system end up if I'm twisted? Well, these pieces are commuted in a particular way, and I need to look at automorphisms which preserve those. And so you end up looking at H bitorsors. So here, so e.g. for Stokes, for Airy that was looked at by Stokes, you would get something like this. And the right way to say that in general is that HI is in a space which is an H bitorsor. It's the H thing. It's a twisted group, which is H twisted around the boundary. And this can be written out explicitly. It's so it's H in GL of this standard fiber at the ith point, so GL of Fi, such that, so it goes back to this condition that the blocks have to be permuted in the same way as the monodromy of the cover. So it's just that H of the ith graded piece, so H of Fi of J has to be equal to Fi of sigma of J, where sigma is the monodromy of the subcover there. So sigma is from I to I. And so this is the so if you for I of BI, so I have this cover I of the ith boundary. I look at the fibers of that. I look at the monodromy of that cover. So this is the monodromy of I over the ith boundary like that. So that gives us certain permutation of the cover, and the H has to permute the corresponding graded pieces in the same way. So you end up with some twisted group, but like this, and so this is an H bitorsor. If I act by block diagonal matrices on the left and the right, it's a principal homogeneous space. Okay, so this picture is slightly more complicated, so let me focus on the untwisted picture and try to get to the statement that we have and see how it specializes to what was known before. So we have this completely explicit affine variety with an action of a group H. So we have H acting on R. And in the untwisted case, I have a map, mu, which goes from R to this product of group H. And this just takes a representation rho to the monodromy around this boundary. So it's really the monodromy of the formal or graded local system. I'm in the untwisted case, so it's just ending up in H. So this is just rho of so just the collections of monodromies around the boundary. So the theorem is that this is a quasi-Hamiltonian moment map. So it just says that R, so I guess that this, in this level, this is this paper in Annals of Math, I think 2014, it was on the archive in 2011 or so. It just says that R is a quasi-Hamiltonian, it's an algebraic quasi-Hamiltonian H space. So with the action of H that we talked about before, the changing of the framing, so with moment map, with group valued moment map in the sense of Alexeyev, Malkin, and Meinrenken, moment map mu from R to H. So I haven't explained what a quasi-Hamiltonian space is. I will do, maybe not today, but at some point. But let me just say, a direct consequence of the quasi-Hamiltonian machine. So basically, it's a multiplicative version of a symplectic structure. You have an H invariant 2 form, and you're able to do symplectic quotients just as in the usual Hamiltonian picture. And after you reduce your slightly more complicated 2 form upstairs gives you a genuine symplectic structure at the bottom. Or if you just quotient without doing the symplectic quotient, you end up with something which is Poisson. And so this just says that R modulo H, the direct GIT quotient, is an algebraic Poisson variety with the symplectic leaves being the symplectic quotients. The symplectic leaves, so mu inverse of C modulo H for conjugacy classes in H. C in H. So this will be a product of conjugacy classes for each of the component groups here. So we're just fixing the conjugacy class of formal monodromy. So this is the direct extension of the results that people had looked at in the tame picture before. So e.g., if you're in the tame picture, so this says that, so theta is equal to n times the tame circle, maybe repeated at each point. Then you get that h is equal to g to the m, and c is in g to the m. And so this is just fixing the usual conjugacy classes. The monodromy of V around each puncture is the same as the monodromy of the thing which is graded trivially by this. So this just says fixes the conjugacy class of V around each puncture, each A. So this is a well-known result that for compact groups, it was in this book of a tier on geometry and physics of knots, and there's a nice expository paper of Michel Audin that talks about the Hamiltonian loop group perspective, which has been looked at by Donaldson and Meinrenken and Woodward, and then that was interpreted more algebraically in this quasi-Hamiltonian perspective that we're extending here. So I had proved this before in the Birkhoff generic picture. So there's the tame case and then there's the generic case. So this means that H is always a torus, but it means more than that, and it means that there's just one level. So it basically means that you've got something like Q, which is like A over Z to the K plus AK over Z to the K plus dot, dot, dot. And the leading term has to have distinct eigenvalues. So AK is in T reg. So this is the generic case, which is basically the case that was looked at by Birkhoff. And this is the case where your Stokes groups can be taken to be alternating full upper and lower triangular unipotent groups. So I proved this a while ago. This is, I don't know, it's on the archive in 2002. I guess this is published in Duke in 2007. So we did this, and then there was the Picala perspective. And then there was this paper written in, I don't know, 2008 that people were interested in these spaces. So we had this idea to go back to extend from the generic pictures to the general pictures. So the first step was this, and then it was extended to the full picture. So the full result is more complicated, and this is in this paper with Daisuke from 2015. So maybe I'll just erase this. So this is probably a bad thing to do. This is on the archive in 2015. So now we have to put in the letter twisted. It's a twisted quasi-Hamiltonian space. And the moment map now does not go to the group, but it goes to this twist of the group. And this can be viewed as a component of a disconnected group having identity component H, but one can axiomatize what happens, and it behaves exactly as before, and you get the same expression for the two form that we had before, and it's possible to prove that R is indeed a twisted quasi-Hamiltonian space with H acting by conjugation, and to get the symplexic leaves, you're fixing. So this has an action of H on the left and the right, and you can look at the conjugation action here, and this is what people call twisted conjugacy classes. And so in fact, the right thing to fix is what they call a twisted conjugacy class here. So the quotient is still an algebraic Poisson variety, and symplexic leaves are got by fixing these twisted classes, which are these H conjugation orbits on this twist of H partial. For instance, something like this, where you could have arbitrary size blocks. Okay, so we get lots of algebraic Poisson spaces. What time am I supposed to stop? I mean, it's probably quite close, isn't it? Let me just draw a picture. I think there's 2 minutes to go. Let me just draw a picture of so the basic proof goes by chopping up the surface into pieces. The classical quasi-Hamiltonian picture has some simple pieces attached to the annulus and a one-whole sphere. And you can then take the fusion product of those, which is just the product of spaces, and build up this global symplexic or quasi-Hamiltonian structure out of the pieces. So the basic job was to work out what you have to do for a single piece. And so I have a disk around the puncher, and so I have a G boundary here, and some H boundary here. So we have this halo as before. We have these tangential punches. So we get this sort of fission space about how to break the group from G to H. And once we have this, we can glue the G boundary here into an arbitrary surface. And so this is like A of theta. So for an arbitrary irregular class, so you just take the space of Stokes representations of this with a base point on each of the boundaries, as we do in general. And so you get something which can be written out explicitly as G cross H partial cross the product of the Stokes group. So let's just call this Sto of theta. This is just the product of the Stokes groups continued back to the base point in a particular way. So it's a very explicit space, so e.g. G cross T cross U plus cross U minus to the K in the generic case. So this is so in the untwisted case, it's a quasi-Hamiltonian G cross H space. And in general, it's a twisted quasi-Hamiltonian space, and mu. So I have data here, something like C, H, and S. So mu of C, H, and S. So it's mu G and mu H. It has these two pieces. This is in G cross H, or perhaps H partial. So this will be mu G is equal to C inverse H. The product of the Stokes matrix is C. So the C corresponds to choosing a particular path like this, and so you would do C, and then you would do the Stokes data, Stokes matrices like this, and then you would have the H, and then you would go back along the path. So that's an expression for the monogamy around the boundary there, as it's supposed to be, and mu H, with a particular convention, it's just the monogamy around the boundary. With the conventions we have, it comes out to be H inverse. So the basic thing one needs to prove is that this is a quasi-Hamiltonian or a twisted quasi-Hamiltonian space, and so we'll have an explicit expression, and we're able to prove that it is, and so we can then put that into this machine to build global spaces out of here. But this is the basic picture that was in Birkhoff's paper, except we're able to upgrade it into this way to view it as a multiplicative symplectic quotient. So we'll talk more about that next time. Okay, I'll stop there.
Do you have character varieties? The representations can sometimes be viewed as invertible elements in spaces of representation of quivers. You also have that picture.
Yeah, so I'm not sure if I'm going to have time to get to that. So what I've been looking at recently, and so for the Panleve 2 picture we had here, you basically had 6 Stokes matrices, and then only 4 of those were independent, and you can view those matrix entries there as a representation of the affine A1 quiver, which is the quiver that Okamoto, it's the root system that Okamoto attached to Panleve 2. It has an action of the affine Weil group of type affine A1. And so in certain cases, it's possible to write down such diagrams in general such that the wild character space is some space of multiplicative quiver representations. Yeah, but I'm not sure if I'll get to that. But I have a number of recent papers, though, that look at that. Perhaps I'll try to mention it tomorrow in more detail. Yeah, but I wanted to start out with the basic. So it's possible to extend all of this to arbitrary reductive groups. I mean, in the papers, it is for an arbitrary reductive group. The quiver picture, you really have to understand in a profound way that GLN is more important. And I only understood that about 10 years after I started to write papers on this. I thought you had to do it all in methods that work for an arbitrary reductive group. And about 2008, I sort of saw that it's actually very interesting to look at things that may only work for GLN, that it is extremely special. Okay.
So let's thank Philip.